In example 5, we're going to find the moment generating function for the uniform distribution. This is kind of nice because the other examples were both discrete distributions. So this is the only continuous distribution we're going to calculate. The others are kind of messy. So even doing this for the uniform distribution is more messy than you might expect, considering that the uniform distribution is so simple. So let me remind you what the uniform distribution is. The density function for the uniform distribution is f of y is always equal to, those three lines mean it's constantly equal to 1 over theta 2 minus theta 1, where y ranges between theta 1 and theta 2. So it's just the constant distribution. That's why it's called uniform. Now let's find the moment generating function. By definition, the moment generating function is colon equals means defined to be the expected value of e to the t times capital Y. Now, the way you calculate the expected value of a function is, well, with the discrete distributions we were studying before, it was a sum. For a continuous distribution, it's an integral. So the integral, this is actually also a definition of expected value, it's the integral of the density function, f of y, times whatever function you're trying to find the expected value of, in this case, e to the ty, dy, and then you integrate that over your whole range for y, which in this case is theta 1 to theta 2. So now we just have to do some calculus. This is the integral from theta 1 to theta 2 of f of y is 1 over theta 2 minus theta 1. That's just a constant there. E to the ty dy. Not such a bad integral. Really not too bad. The answer is 1 over theta 2 minus theta 1. That's a constant, so I can pull it out. Now, what's the integral of e to the ty? Remember here, our variable is y. We're integrating with respect to y. And so the integral of e to the ty, if you do a little substitution there, I'm going to go ahead and do it in my head. It's just e to the ty times 1 over t. That's because we're thinking of t as being constant here. Y is the variable of integration. So it's just 1 over t. If you took the derivative of that with respect to y, you'd get back to e to the ty. And we want to evaluate that from y is equal to theta 1 to y is equal to theta 2. So we get 1 over, I'll combine the t and the theta 2 minus theta 1, theta 2 minus theta 1. And now we have e to the, we're plugging in these values for y, so e to the theta 2 times t minus e to the theta 1 times t. I need some parentheses here. And I could write that over a common denominator, e to the theta 2t minus e to the theta 1t. And we divide that by t times the quantity, theta 2 minus theta 1. That's my moment generating function for the uniform distribution. Notice that this is a function of t now. There are no y's anywhere. That is what is supposed to happen with a moment generating function. It should always be a function of t, should not have any y's anywhere in there. So this is my complete answer here. And I'm done with that example, except for maybe a quick recap of the steps there. Just to remind you, we had a whole lecture on the uniform distribution, so if you don't remember the sort of basic premise of the uniform distribution, you could go back and do a quick review there. But the density function is 1 over theta 2 minus theta 1. In particular, it's constant. That's why I have 3 lines here to show that it's always equal to. The range goes from theta 1 to theta 2. The moment generating function, by definition, we learned that in this lecture, is the expected value of e to the ty. The expected value of any function is the integral of the density function times that function. If this were discrete, we'd have sigma sign, a summation, instead of an integral, and we'd have a probability function p instead of a density function f. But it's really the same idea. So when you look at these formulas, if you kind of blur your eyes a little bit, you should see how they're really the same idea. Integral is like adding things up. The probability function is kind of the analog of the density function. So instead of the summation of p of y, we have the integral of f of y, and then we still have e to the ty. F of y from above is just 1 over theta 2 minus theta 1. That comes from up above, and we'll pull that out since it's a constant. Now we have to integrate e to the ty. I did a little u substitution. My u was ty, and my du was t dy, and so dy was 1 over t du. That's where I got that 1 over t from on the outside there. It's sort of the opposite of the chain rule or a substitution. So we still have e to the ty. That's because we're integrating with respect to y, not with respect to t. Now the range on y goes from theta 1 to theta 2. So I plug those in, and I still had 1 over t times theta 2 minus theta 1. And it simplified down. Well, it's still quite complicated considering that it's the uniform distribution. You might expect something simpler for the uniform distribution, but you end up with this function of t that does represent the moment generating function for the uniform distribution. I'm not going to take this one any farther, but if you wanted to, you could use this to find the mean and the variance of the mean and the variance of the uniform distribution, the same way we did in example 4 with the Poisson distribution. You could calculate those out. It gets a little messy, so I'm not going to do it here. Instead, I'm going to wrap up this lecture here on moment generating functions. This is part of the probability lecture series here on Educator.com. Next up, we're going to talk about bivariate distributions. So we'll have a y1 and y2. That's another whole chapter of excitement, and I hope you'll stick around for that. You are watching probability lectures on Educator.com. My name is Will Murray. Thanks very much for joining me. Bye-bye.